Hello there, STAT216ers, and welcome to another RStudio video. In this video, I'm going to show you how you can calculate confidence intervals in RStudio. And in this video, we're going to assume that we're working with a sampling distribution that is normal and focus primarily on sample proportions and population proportions in this case. But what we're going to talk about applies more generally by tweaking some of the details just a little bit, and we'll see that in another video, I believe. So let's remind ourselves what confidence intervals are. First and foremost, they're a tool that we can use to estimate population parameters from sample data. So to route this to an example, we could investigate a population proportion using a sample proportion. And instead of providing only a point estimate, our goal is to provide a range of plausible values for the population parameter instead of simply just a point estimate. Now, this range of values is going to end up being determined by three different quantities. The point estimate of the population parameter. So in our example that we're working with now, this will be the sample proportion. Our range of values is going to have to incorporate variability due to sampling. Now, if we think about where that comes from, that's the standard deviation of the sampling distribution, otherwise known as the standard error. One other thing we need is a confidence level. In other words, we want to specify how confident we want to be that our range of values encapsulates the true population proportion. The confidence level determines what we'll end up calling a critical value, and that critical value will end up determining the width of our confidence interval. Broadly speaking, the formula for a confidence interval will always be the same, and it's going to be your sample statistic plus and minus the critical value multiplied by the standard error. And in the rest of the video, we'll see how we can calculate the sample statistic, find the critical value. This is an area where students seem to struggle, and also we'll find the standard error for our particular example. But broadly speaking, a confidence interval is always sample statistic plus or minus critical value multiplied by standard error. Great. So where do the confidence intervals come from? Well, the most common ones are 95, 90, and 99%. But as you'll see in the homework, you can use any confidence level you'd like. Now, if we think about what we're saying, we want to be more, if we have a larger confidence interval, or a higher confidence level, we want to be more sure or more confident that our interval will capture the true population parameter. If we want to be more confident in that, the interval itself needs to be wider. We need to encapsulate more values to be more confident in capturing that interval. So a higher confidence level means that our confidence interval must get wider. And you can see from that little hand gesture there that there's going to be a trade-off between a confidence level and a useful estimate. If your confidence level is too wide, you can provide a useless range of values. And there are some funny cartoons based on that in the book and elsewhere on the internet. All right. How can we use the confidence level to determine the width of our confidence interval? So the normal curve I have drawn on here is the width of a normalized, demonstrates the width of a normalized 95% confidence interval. And we don't have the values labeled here, but really what's going on is that we're finding a range of values so that 95% of all samples fall in this area. Now, the idea of a confidence interval is that if you have an interval that falls in this range of values, so if you have a sample that falls in the blue area and you form a confidence interval that has the width of the blue area, then that confidence interval will capture the true population parameter. So what that means is that any confidence interval with the width of the blue area here, this area on the bottom, if it has the width of the area on the bottom, of all of those confidence intervals, 95% of them will capture the true population parameter. That's great. Well, how can we use this idea to actually find the bounds, what we recognize is that the width is coming from saying, okay, this is some number of standard deviations above and below the mean. How can we use this idea to actually determine the bounds of this area? Well, we have an area and we want a z-score. So we have a probability and we want a z-score. That's exactly what the qnorm function in RStudio does. So we can use the qnorm function to determine the critical value from our confidence level. So how can we find that confidence level, or that critical value, sorry. So say we want to start out with a p% confidence interval. And this will apply more broadly to other distributions, but we're going to also suppose that our sampling distribution is normal. So the critical value is the z-score, we'll call it k, so that p% of all sample statistics fall within k standard deviations of the mean. Going back to the previous slide, what we're trying to find is the value here. It looks like it's just a little bit below 2, so that 95% in this case of all observations fall within that number of standard deviations from the mean. This is normalized so that the mean of our distribution is 0. Okay? That's what we're looking for, is we're looking for the number k, or the z-score k, so that p% of all sample statistics fall within k standard deviations of the mean. Great. If that's the case, then the area in the tails of the distribution is 1 minus p. So the upper and lower tails each have area 1 minus p over 2. Going back to this is saying that the non-shaded area in this graph has area 0.05, which means that the upper tail has area 0.025, as does the lower tail. Great. So to find the critical value, we can use the qnorm function, and we want to take 1 minus the confidence level, which we're saying is p here, and we want to take that confidence level as a decimal, or rather than as a percentage. And we want to use the lower dot tail equals false option on qnorm. Why is this? Well, if we look at an example for 95%, if we do 1 minus 0.95 over 2, that gives us 0.025 like we claimed. And now if we do qnorm of 0.025, that gives us negative 1.96 out. But if we set lower dot tail equal to false, it'll give us the same value, just the positive version of that. So setting lower dot tail equal to false gives us the z-score so that 2.5% of all measurements fall above that particular value. So it gives us the z-score for the upper tail here. And that just makes our life slightly easier to take the positive z-score rather than the negative. Okay, so we can use this schematic of using qnorm to find the critical value now for any confidence level we'd like. Great. What's next? Well, let's look at some common critical values. And again, here we're assuming that the sampling distribution is normal. In Chapter 7, we'll deal with some distributions that are not normal, and the critical values will change because we're not dealing with a normal distribution. But if you want to calculate a 90% confidence interval, your critical value is about 1.645. For 95%, it's about 1.96, and for 99%, it's about 2.56, roughly. And the thing that we want to notice here is that as our confidence level increases, the critical value increases. That's because what we're finding is the number of standard deviations above and below the mean you need to look in order to encapsulate whatever percentage of samples we're looking at. So for a 99% confidence interval, this is saying that if you look 2.58 standard deviations above and below the mean, that'll encapsulate about 99% of all samples, which is quite a lot, of course. So as the confidence level increases, the critical value increases, and that will mean that, as we expected, our confidence interval will get wider and wider to create a larger range of values. All right, now let's actually go through an example of calculating a full confidence interval in RStudio. And I have the code up here, but we'll go through that code in my R terminal together to see what's going on with it. So in our example, we took a random sample of 250 Americans, and we're going to suppose that 82 of them believe that cheese is a healthy food. We're going to try to calculate and interpret a 93% confidence interval for the proportion of Americans who believe cheese is healthy. Okay, the first step is we want to calculate the sample statistic. In this case, that's the sample proportion. So I'm going to call it p hat. It's not fat like they called it or like they spelled it in the late 90s and early 2000s. But what do we also need? We need the standard error. And since we're looking at a sample proportion, the standard error is going to be the square root of the sample proportion times 1 minus the sample proportion divided by the sample size. So that's the standard deviation of the sampling distribution. Let's take a quick look at our sample proportion, 0.32. Great. I'm going to just copy and paste this standard error calculation in here. So what's our standard error calculation? It's about roughly 3%. So that means that if we were to repeatedly take samples of 250, we'd expect a variation in sample proportion of about 3% per sample. Now to find our critical value, we want to use the same schematic as before. So it's 1 minus 0.93 divided by 2, and we want to set our lower tail equal to false. Let's copy and paste this. Let's think about what there should be. So our confidence level is just a little below 95%. So that means our confidence interval is going to be slightly narrower. And if it's slightly narrower, that means our critical value should be slightly smaller. And low, there it is. It is just a little bit below the 95% confidence interval's critical value. Great. So now the last line I have here kind of does everything all at once, but let's unpack this step by step to see what it's doing. So if I copy and paste this here, you'll see that it spits out exactly what we have down here. And we see that we're 93% confident that the proportion of Americans that believe cheese is healthy is between 27.2 and 38.2%. There's a typo on my part on this last percentage here. But let's just quickly unpack what this is doing. So this is taking the sample proportion, which is our p hat, and this command is saying add and subtract. So we want to subtract first, then add the critical value multiplied by the standard error. And then for displaying purposes, I wanted to round to 5 decimal places. So if we want to do this one at a time, we could also do p hat minus the critical value times the standard error. And we can also do p hat plus that value and get the same values. But if you store these values, if you store each of these pieces in RStudio, it makes calculating confidence intervals quite easy. You can also go up and change the confidence or the confidence level relatively easy to see how this changes in context. So say instead we wanted a 97% confidence interval. All we would need to do is change the confidence level in this guy. I scrolled up using the up arrow on my keyboard to get back to this critical value command. Hit enter, and then we can go back and calculate our new confidence interval and notice that, our confidence level increased, so our interval should get wider, and that's exactly what we saw. Great. What's next? This little outline should be pretty helpful in working on your homework. So what do? Again, you find your sample statistic, you calculate your standard error, you find your critical value, and then you can use those, chunk them all in together, and find your confidence interval. The last thing I wanted to do is show you a bunch of different confidence intervals for the same estimate. So this is all based off the same data from before, but our confidence levels are going to increase. So we're starting with an 80% confidence level, a 90% confidence interval, 95% confidence interval, and a 99% confidence interval. The left number here is our lower bound, the lower bound of our confidence interval, and the right is our upper bound. So as we increase our confidence level, notice that our lower bound is decreasing. That's saying that the confidence interval is getting wider on that side, and the upper bound is also increasing. So the lower bound decreases and the upper bound increases, giving us a symmetrically wide confidence interval. One thing to notice is that as the confidence level changes, the standard error stays the same. The sample statistics stays the same. Really, the only thing that changes in the calculation is the critical value. So we really see through this example that the critical value is the thing that's making our confidence intervals wider and shorter, because it's the only thing that's actually connected to the confidence level. Great. Last up, we have a visualization of those same confidence intervals. So the x-axis is the proportion that we're investigating. The red bar represents, or the red line through the middle of this graph is the point estimate. So this is the 38.2% that we're using as the center of our confidence intervals. And then each of these horizontal bars represents a different confidence interval at different confidence levels. And we can see that as the confidence level increases, again, the confidence intervals get wider and wider and wider. Hopefully this gives you a little bit of a better understanding about confidence intervals and helps you calculate confidence intervals using RStudio. In the future, we'll see some tricks for calculating confidence intervals from datasets directly, but that takes a little bit more doing and requires you to start with a dataset rather than just summary statistics about your data. Thanks for watching. Hopefully this was informative. Have a good one, and we'll see you soon.